Hey everyone, my name's Angel, and in this video we're going to be going through our second problem that discusses work energy theorem. And in this scenario we've got a woman driving a motorcycle with a combined mass of 70 kilograms traveling at 30 meters per second. If the woman slows down to a speed of 15 meters per second by applying the brakes, how much force was exerted by the brakes if the change in velocity occurred in a 12-meter displacement? So before tackling this problem, I just want to talk to you again about the work energy theorem real quick and why it makes sense that it applies to scenarios such as this. So the work energy theorem, if you recall, and we spoke about it in our last video if you need to go back, is discussing how the net work on an object is equal to its change in kinetic energy. And so if we were to draw out that equation, it reads as so: the net work of an object is equal to its change in kinetic energy. So why does it make sense that the net work is equal to a change in kinetic energy? Well, if we look at our work equation, we know that when you have work on an object, you have to have force and you have to have a change in displacement. So essentially you have to put a force, either a push or a pull, and the object has to move, and that will give you work. And when you have force, according to Newton's second law, you have acceleration, because force is directly proportional to mass and acceleration. And when you have an acceleration, you have a change in magnitude of velocity or a change in direction of velocity. And so that goes back down to here. And so that's how we make sense of the work energy theorem. And you can actually see it in all of the fundamental equations that we learn in physics up to this point. So I just think that's pretty cool, but let's go ahead and see how this applies to this question here. Well, we've got a change in kinetic energy because we're going from 30 meters per second to 15 meters per second, right? So we've got our change in kinetic energy. And once we solve for that, we have our net work. So we've got this net work. And then now that we've solved for that value, we can set that net work value equal to our work equation. And we have our 12-meter displacement here. So then the only thing we would need to solve for is the force. And so I think that could be said to be pretty straightforward, but I think what stops a lot of students is that they have a lack of understanding for the conceptual basis of the work energy theorem, or just how equations relate to one another. And so before we do the math for that, I just want to talk about one more thing, and that's why we aren't considering the force of friction on the tire. Because if you were to imagine the scenario, you've got the tire, I'm going to draw that in black. You've got the tire, and so if you're slowing down, you should have some force of friction on there, and we should be considering that into the work energy theorem, should we not? Well, not in this case, and that's because we're talking about the brakes. So what I drew right there in the middle of the tire, the middle of the wheel, is the rotor. And then I'm going to draw the brakes on here. And so the brakes, in order to slow down the wheel, apply directly to the rotor. So we're looking at the force applied by the brakes on the rotor rather than the force of friction applied to the tire and how it slows it down. That's actually a whole different type of scenario. But in this case, we're looking at the force of the brakes applied on the rotor to slow down the motorcycle. And so now let's take a look at the math. And as we've discussed, we are going to be utilizing the work energy theorem because we have a change in kinetic energy occurring. And that change in kinetic energy is going to be going from 30 meters per second to 15 meters per second. And just keep in mind that the change in kinetic energy is the final minus the initial. And so that's the change in, that's what that delta means, is final minus initial. And it doesn't just go for kinetic energy, it goes for a lot of other concepts as well. So in this case, we've got the work net is equal to the final, which is 15 meters per second. So we got 1/2 m, which is 70 kilograms, and 15 meters per second. And we're going to square that because that's 1/2 mv squared minus 1/2 mv squared 30 meters per second was our initial. So sorry that's kind of messy, but what we notice from this is that we're going to have a negative value because the speed in our final is smaller than the speed of our initial. So we're going to have a negative value for our net work. And why does this make sense? Well, if we're slowing down, it makes sense that we are having a negative force, a negative work being applied. In this case, the brakes are causing the motorcycle to slow down, and it makes sense that would be considered negative rather than speeding up, which would be considered positive. And so generally I try to give you guys values that are pretty simple to solve, but in this case I wanted to make it somewhat realistic, and these are the values that I was able to come up with. So we will be using a calculator for this problem, and we get that this first value, when we square 15,225 times 70 divided by 2, is exactly 7,875 joules. And then when we do same thing for the 30 meters per second, we get 31,500 joules. So that's a pretty big difference. Doubling the velocity or doubling the speed, it gave a pretty large difference there. And so we get that our net work is equal to negative 23,625 joules. All right, so now, but that's not what we're looking for. That's just part of the problem in order to solve for the force on the brakes. But we know now, because of the work energy theorem, that change in kinetic energy, those negative 23,000 joules, are equal to the net work. And so the net work is the summation or the difference of all of the work forces being applied onto the motorcycle. And we discussed in this case how the brakes are applying to the rotor, and it's the only work that is being applied. So we can say the work on the brakes, the work on the rotor from the brakes, WB, is equal to this negative 23,625 joules. And then work, because that's the only work, we know that the work from the brakes is also equal to the force times the displacement. And we're given the displacement in the problem, and that's 12 meters. And so we're going to substitute in here 12 meters for the displacement. And then when we divide 23,000 joules, 23,000 so on, by 12, we get that the force from the brakes is equal to 1,968.75 joules. Now on the MCAT, you'll probably get something close to 2,000, and then you'll get some other options that aren't even close to 2,000, and so that would be the better choice of them all. And that's in newtons. You got to keep that in mind for sure. And so that is the force, and that should be negative, I'm sorry. That is the negative force applied from the brakes that are causing the motorcycle to slow down, or in other words, decelerate. And that's what comes all back to the work energy theorem. And even with this force, I just want to remind you, even with this given force now, because we have the mass as well, we could even solve for the acceleration of that process, because we have the force from the brakes and we have the mass of the woman, so we could solve for the acceleration in a negative direction that was part of the scenario. All in all, I hope that made sense conceptually to you. We want to show you a lot more than just the math, because although the math is important, understanding the conceptual part is really what makes it difficult for most students. So if you have any questions or any comments, go ahead and leave them in the comment section below. We really encourage you to subscribe so that you can receive the videos as we are making them. And also we appreciate any likes or positive feedback that you have on how we can make this better. Thank you.